groups acting asymmetrically on hyperbolic spaces. So I'm going to talk about a large portion of this famous bright-city universe. My goal will be to convince you that this is indeed a large portion of the universe of finitely presented groups. So there are a lot of examples there, but the lions are still not there. So they can still prove something about this class of groups. And today I'll review some examples after talking about basic stuff. And during my next lectures, I'm planning to talk about what you can do with acylindrical hyperbolic groups. I think I'll say a few words about small transformation theory, maybe about dent fitting, group theoretic dent fitting, and also about some new stuff which is based on my joint work with Caroline Abbott and Derek Hill. Okay, so let's start. Do we want to see the definition of acylindrical action?
Yes.
Okay, so let me start with basic things. So I guess nobody needs to know what a hyperbolic space is. I just want to remind you that given a hyperbolic space X, by dx I denote the boundary of the hyperbolic space, and this is the sequential boundary. So it's defined in terms of sequences of points converging to infinity, not in terms of that as a trace. And these are two different definitions, right, as you know, in the case of non-proper spaces. So I don't assume my hyperbolic spaces are proper or whatever. Now, if you have a group which acts by isometries on a hyperbolic space, the space is hyperbolic, the action extends to the action of the group on X using the boundary of X. And there is a standard classification of elements of the group. So an element G in G is called elliptic. If the cyclic subgroup generated by G has bounded orbits, and loxodromic or sometimes hyperbolic, if the map n goes to G to the n x, where little x is some base point in my space, gives a quasi-isometric embedding from Z to X. So this is equivalent equivalently, this is the same as saying that there exists some epsilon greater than 0 such that the ratio, the distance in X between little x and G to the nx divided by n is greater than or equal than x. The translation number is positive. So all other elements are called parabolic. So actually that's a theorem, but you can think of it as a definition. Now for every loxodromic element, G and G, you have exactly two limit points on the boundary. So G fixes, let's say it this way, exactly 2 points of the boundary. And we denote these points by G plus and G minus. G has the so-called north-south dynamics on the boundary, which means that if you exclude a little neighborhood of this point, then everything else is pushed by G inverse to G G minus, and if you exclude the little neighborhood of this point, then G pushes everything else to G plus.
What's the metric on the boundary?
What's the metric on the boundary? Well, it's induced by the metric on X. I mean, there are several ways to metrize the boundary, but well, one way is to use Gromov product. It's not so trivial to write a precise thing, but locally it's locally it's defined in terms of Gromov boundary. Gromov product. So, what else do we need to know? So we say that lexicodromic elements G and H from G are called independent if G plus minus intersects H plus minus trivially. So the limit points or fixed points on the boundary are trivial. So that's all what I want to say about the terminology. Now I want to remind you the classification of actions of hyperbolic spaces, which is due to Gromov. So there will be 5 types of actions which can be classified in terms of the set of limit points on the boundary. So let me remind you that if you have a group G which acts on a hyperbolic space X, then we define the limit set of G as the set of accumulation point of any orbit on the boundary. So you take any little x, any base point, you take the orbit of x, okay? So this is just the orbit of x, you take the closure, because this is the closure in x union the boundary, and you intersect with the boundary. That's the set of limit. It's independent on the choice of the base point. That's easy to see from hyperbolicity. Okay. Now, if you can also characterize actions in terms of lexicodromic elements, and some actions can be characterized in terms of orbits, whether they are bounded or not. And some actions can be also characterized in terms of the number of fixed points of the group G on the boundary. So the set of fixed points is the set of all G in G such that Gy is y for every, the set of all points y in the boundary such that Gy equals y Well, so the first type of actions is called elliptic. And this is the only action which can be uniquely characterized by orbits. So orbits are bounded for an elliptic action. There are no limit points for the boundary. There are no lexicodromic elements. The set of fixed points can be arbitrary, maybe any, or this group may fix the whole boundary. There are no restrictions. So the second type of actions is called parabolic. So there is one are unbounded. And the set of fixed points coincides, well, with the limits. So every finitely generated or even every countable group admits a proper parabolic action on a hyperbolic space exercise. Parabolic actions are abundant if you just request the existence of some action with unbounded orbits on a hyperbolic space. It's not going to restrict your class of groups. Number 3, now the next type of actions is called lineal. So we have 2 limit points on the boundary. There is one loxodromic, well, there are loxodromic elements here, but they're all dependent. So yes, there are loxodromic elements, and for every loxodromic elements f and g, in G, f plus minus is the same as g plus minus. Well, up to changing the order. So for me, g plus minus is the set consisting of g plus and g minus. Okay, so orbits are unbounded, and the set of fixed points coincides with the 2 limit points on the boundary. So the typical example is a cyclic group generated by one loxodromic element, but there are of course non-cyclic examples because we don't require the action to be free or whatever. Number 4, now these 3 types of actions are called elementary. Now the next 2 types of actions are called non-elementary. So this action number 4, the non-elementary action, splits into 2 types. First is called quasi-parabolic. And the quasi-parabolic action, so here we have infinitely many limit points. Now there are loxodromic elements, but for any 2 loxodromic elements, they are dependent, which means that f plus minus intersects g plus minus non-trivially. There are no independent loxodromic elements. So in fact, the orbits of course are unbounded because we have loxodromic elements. In fact, there is a single point. Remember, this column corresponds to the fixed points. There is a single point on the boundary which is fixed by all elements of the group, in particular by all loxodromic elements. So the typical example to think about is the action of the bound-slug solitary group on its bus ser 3. So you know that this group is an ancient extension of Z, and you take the associated bus ser 3. So this BS means different things about this BS. And that's a quasi-parabolic action. Fixes one point on the boundary of the tree. And if you want an example of a parabolic action, just take the commutant of this group. And the commutant of this group has parabolic action on the same tree. Doesn't have loxodromic elements. That's an exercise. And finally, you have general type actions. You still have infinitely many limit points. Here you have loxodromic elements, and there exist loxodromic elements f and g such that they are independent. So f plus minus intersects g plus minus trivially. In fact, in this case, there exist infinitely many independent loxodromic elements. So orbits are again unbounded, and the set of fixed points is is empty in this case. So these are 5 actions. Now the theorem, which is due to Gromov, is that if G acts by isometries, all actions on spaces are supposed to, or metric spaces are supposed to be isometrical by default. So if G acts by isometries on a hyperbolic space X, then exactly one of the possibilities 1 through 5 happens. So every action on a hyperbolic space is of one of these 5 types. Now, questions?
I'm just going to see what that's empty.
The set of fixed points again. Nothing is fixed. So the second theorem by Gromov classifies geometric actions. So if G acts on a hyperbolic space X and the action is geometric, so geometric is proper and co-compact, or proper and co-bounded, which is not important for us. So if you have a geometric action, for example, if you have a hyperbolic group acting on its own Kelly graph, then exactly one of, so there are only 3 possibilities: elliptic, linear, and general type. What is linear? 3 or 5 poles. Moreover, G is finite in case 1 and virtually cyclic in case 3. So in this case, in addition, you have characterizations of groups which can act elliptically and linear. Well, in general, of course, it's not true because you take action of any group which is just trivial, just fixes everything. And this is an elliptic action. There are no restrictions on the group whatsoever, right? But in case the action is geometric, if G acts elliptically, it must be finite. And of course, you can have linear actions, just take, say, direct product of any group you like, and Z, take the standard action of Z on the real line, induce the action of this product by going through the action of Z. That's a linear action, but the group is not virtually cyclic. So this is a non-trivial result. Now, that's all I wanted to say about general hyperbolic actions. Now let's talk about acylindrical actions, which are somewhere between general actions and geometric actions. So every geometric action is acylindrical. Just to remind you, although you already had a chance to learn the definition of an acylindrical action, let me just remind you that the action of a group G on a space X, not necessarily hyperbolic, just any space, is called acylindrical if for every epsilon greater than 0 there exists R and M constants such that for every x y in X such that the distance between X and Y is at least R. If you look at the number of elements of your group that almost fix X and Y, so the distance between X, Gx is at most epsilon, and the distance between y and gy is at most epsilon, then this number is at most n. So here is the picture, which you'll probably see again several times. So this is my x, this is my y, and the distance between them is large. And then you look at all elements which fix x up to epsilon and y up to epsilon. So this is at most epsilon, that is at most epsilon. And there are only finitely many such elements G. So in other words, for all but finitely many elements G, if G almost fixes x, it should move y a lot. You can think of this as some sort of properness for the action of G on x cross x minus a thick diagonal. So when you exclude elements within small distance from each other, basically you exclude thick diagonal. So this notion is Brian Baldich, and the whole theory of acylindrically hyperbolic groups started from his paper when he proved that mapping class groups act acylindrically on the curve context. So I'll mention this later. Okay, so now know what acylindrical action means. So I can tell you the classification of acylindrical actions. Well, examples. Well, the first thing you have to understand is that if G acts on a bounded space, say on a point, then it's an acylindrical action for the stupid reason, just there are no points far away. So you have to require some sort of non-triviality of this action in order to restrict the class of groups. Second, if you have geometric action, which means proper and co-bounded, that every such an action is acylindrical. But if you have a proper action, then it does not follow that the action is acylindrical. So you do need the action to be co-compact to derive acylindricity. And the reason is that if you take the definition of a proper action, there is nothing uniform there. You just request something to be finite, while in the definition of acylindricity, you have some sort of uniform finiteness. And that uniformness doesn't follow. So if you replace n with infinity, just request that this is less than infinity, then it follows. But this uniform version doesn't. As I said, every group has proper parabolic action, every count has proper parabolic action on hyperbolic space that can be used to find an example of proper action which is not acylindrical. Okay, so now there is a classification of acylindrical actions, possible acylindrical actions on hyperbolic spaces. And the classification is this. If the group G acts acylindrically on a hyperbolic space, then exactly one of the following three possibilities holds. So the first possibility is that the action, let's call it x, G on x is elliptic, which means has bounded orbits. The second is that the action on x is linear. And in this case, G is virtually cyclic. And the third possibility is that the action is of the general type. So let's compare this result to the two results we had before. So first of all, if you compare it to the result about classification of all possible actions, what you see that parabolic actions and quasi-parabolic actions are prohibited. They cannot be cylindrical. That's first observation. Second observation is that in case of the lineal action, we do have the same characterization as in case of geometric actions. Only virtually cyclic groups can have this sort of action. So the first two cases correspond to elementary actions, and this case is non-elementary. So in particular, it follows from this theorem that non-elementary acylindrical actions on hyperbolic spaces can be characterized very easily. So an action of a group on a hyperbolic space, an acylindrical action, is non-elementary if it has unbounded orbits, which rules out the first possibility, and the group is not virtually cyclic, which rules out the second possibility. You don't even need to know anything about boundary points. Well, one thing which you can derive from here is a corollary, which was, well, it's a corollary from this theorem, but it was proved before this theorem was proved by Brian Bowditch, which says that every